In this video, we will go over some basic related rates problems so we can establish a solid foundation. Problem number 1. A particle travels along the curve y equals the square root of x. At the moment when the particle is at 9, 3, it is given that dx dt is equal to 7 units per second. Find dy dt at the same moment. First, scan through the problem for any rates that you are given. We are given dx dt is equal to 7 at this particular moment. So let's write that down. dx dt is equal to 7 units per second. We also know that we are looking for dy dt. So I'm going to write that down as well. dy dt is equal to question mark. So these are the rates that we either have or we have to find. What else are we given? Well, I see that we are given the point 9, 3. That means that x is equal to 9 and y is equal to 3 at this particular moment. So this is everything that we are given. And in this straightforward problem, we are told the relationship between x and y is y equals the square root of x. Sometimes we have to come up with these relationships on our own, but they were nice enough to just give it to us. I'm going to rewrite this slightly as x to the 1/2 power. Now let's take the derivative of both sides with respect to t, because that's where the dx dt and the dy dt will come from. So I'm doing a d dt on this side and a d dt on this side. None of these variables match, so we will have to do the chain rule each time. Well, actually, so for this first one, it's just a single variable. So that's just dy dt, and that's it. But for this one, we will move that 1/2 in the front. Subtracting 1 gives us negative 1/2 power. But then, the chain rule, we multiply by dx dt as we take the derivative of the inner function. So we have this. Let's simplify this a bit. I think I will put this back in the form with the square root of x in the denominator. So we have dy dt is equal to 1 over 2 times the square root of x dx dt. So let's look back at our inventory and see if there's anything that we can substitute. So we are looking for dy dt, but we are given dx dt. It's 7. So I'm going to substitute 7 for dx dt. So I have dy dt is equal to 1 over 2 radical x times 7. Oh yeah, we're also given x is 9. So let's make that substitution as well. The square root of 9 is 3. 3 times 2 is 6. So we will have 7 over 6. And this will be units per second. All right, that's it for problem number 1. Number 2, let's try it with a trig function. A particle travels along the curve y equals cosine x in such a way that dx dt is always 2 units per second. As the particle travels through some point P, we have dy dt is equal to radical 3. Find all possible x coordinates of point P, given x between 0 and 2 pi. Then find the corresponding y coordinate for each point. That was a lot of information. Let's first scan through, looking for any rates that we are given, or any rates that we need to find. We are told that dx dt is always 2 units per second. So let's write that down. dx dt is always 2 units per second. Any other rates? Well, at the moment that the particle passes through point P, that was a lot of P's, dy dt is equal to radical 3. So let's write that down as well. So we have dy dt is equal to radical 3. We are not looking for any rates. We are looking for x and y coordinates. And I believe these are all the facts that we are given. We are also given the relationship. So let's go ahead and write that down. So we have y is equal to cosine of x. So let's take the derivative of both sides with respect to t. So d dt, d dt. On the left, that just gives us dy dt. On the right, we will do the chain rule. The derivative of cosine is negative sine, so we write negative sine x, but then we will multiply by the derivative of the inner function. In other words, we multiply by dx dt. So let's look at our inventory. We are given that dx dt is 2, so let's plug that in right here. And dy dt is radical 3, so we're going to plug that in right here. So we have radical 3 is equal to negative sine x times 2. All right, so dividing both sides by 2, we have radical 3 over 2 is equal to negative sine x. Dividing both sides by negative 1, we have, and I'm going to switch it around in the way that I am more comfortable. So we will have sine x is equal to negative radical 3 over 2. So ignoring the negative sign for a second, the sine of what angle is radical 3 over 2? Well, that is pi over 3. We know that the sine of pi over 3 is negative radical 3 over 2. Actually, I'm not going to write this down right here because this simply tells us the reference angle. And I think I will do my thought process off to the side. We know that the reference angle is pi over 3. Between 0 and 2 pi, there are 4 angles with a reference angle of pi over 3. There's one in every quadrant. We want the sine function to be negative, however, and that means we are talking about the third and fourth quadrant. So we can forget about this angle and this angle. So x could be, and this is 3 pi over 3, all right? Pi is the same as 3 pi over 3. 2 pi is the same as 6 pi over 3. That helps me remember that this angle right here is 4 pi over 3. And this angle over here is 5 pi over 3. So we have the x values, we just need the y values to go with them. But remember, we are talking about y equals cosine x. Which means if x is 4 pi over 3, then y is cosine of 4 pi over 3. And cosine of pi over 3 is 1/2. 4 pi over 3 is in the third quadrant. This is 3 pi over 3, so 4 pi over 3 is past that. Cosine is negative over here, so negative 1/2. Also, y is equal to the cosine of 5 pi over 3. Again, cosine of pi over 3 is 1/2. 5 pi over 3 is over here. All right, this is 6 pi over 3, so this is 5 pi over 3. Cosine is positive over here, so we will have positive 1/2. So we have the points 4 pi over 3, comma, negative 1/2, and 5 pi over 3, comma, positive 1/2. Number 3, the side length of a square increases at a constant rate of 5 centimeters per second. At the moment when the square's area is 36 square centimeters, find the rate of change with respect to time of the square's area. Indicate your units in your answer. Let's start by listing out any facts that we are given. So the side length increases at a constant rate of 5 centimeters per second. They didn't give me any variables, so I'm going to define one. Let x equal the side length of the square. So this side length increases at a constant rate of 5 centimeters per second. That means that dx dt is going to equal 5 centimeters per second. They gave us another fact in the second sentence. We are talking about the moment when the square's area is 36 square centimeters. So the square's area is equal to 36 square centimeters. Those are the only facts we have. So what are we looking for? Find the rate of change with respect to time of the square's area. So we are looking for dA dt. The two quantities that we are dealing with are the side length x and the area a. So we need a relationship between the side length and area. And of course, we know that the area of a square is going to simply be the square of the side length. So a is equal to x squared is the relationship. Let's take the derivative of both sides with respect to t. So on the left, we have dA dt. And then on the right, because these variables do not match, we will have to do the chain rule. So the derivative of the outer function is 2x, but then we multiply by the derivative of the inner function, which is dx dt. Let's scan back through our inventory and see if there's anything that we can plug in. So we are told that dx dt is equal to 5. So I can put a 5 in right here. We are given that the area at this particular moment is 36 square centimeters, but we don't have a simple area anywhere in this formula. So I'm going to come back to this. And we are looking for dA dt. So really, so far, this is what we have. dA dt is equal to 2x times 5. So we need to find dA dt, but we still have this variable x sitting here. So we need to find x somehow. Well, we haven't used this 36 yet. We know the area at this particular moment. And we have the relationship that the area is equal to x squared. So let's use this to find x. So if the area is, of course, equal to x squared, but we know at this moment that the area is 36, so we have 36 is equal to x squared. Then taking the square root of both sides, we know that x is equal to 6. And now we can substitute that in. So we know that dA dt will equal 2 times 6 times 5, which is 60. Let's not forget the units. This is the change in area divided by the change in time. And we were talking about centimeters. So this will be centimeters squared, that's your area, per second, that's your time. And that is your final answer. Last problem. The volume of a cube decreases at a constant rate of 1 cubic foot per minute. At the moment when the cube's volume is 27 cubic feet, find the following. Before we start the inventory, let's define a couple of variables. Let's let x be the side length and let v equal the volume. So we are told that the volume decreases at a constant rate of 1 cubic foot per minute. So that is telling us that dv dt is equal to -1 feet cubed per minute. The negative sign is because it says it decreases. Also, this problem occurs at the moment when the cube's volume is 27. So we know that V is equal to 27 cubic feet. So what is it that we are trying to find? Find the rate of change with respect to time of the length of one of the cube's edges, which we have called x. So we are trying to find dx dt. Now that we have our list of facts, let's come up with a relationship between them. So we need a relationship between volume and the side length. So we know that the formula for the volume of a cube, if the side length is x, the volume is x to the third power. So let's take the derivative of both sides with respect to t. So d dt and another d dt. So on the left side, we now have dv dt. And we will have to use the chain rule over here because the variables do not match. So this will be 3x squared for the outer formula. But then we multiply by the derivative of the inner function, which is our dx dt. So let's look back through our inventory and see if there's anything that we can substitute. So we know that dv dt is -1, so we can put -1 in right here. We know that the volume is 27. That doesn't directly show up here. And then we just have 3x squared. I'm just going to leave a space here for a minute, times dx dt. We are looking for dx dt, so we can't have any other variables. So we somehow need to find the value of x. And guess what? We haven't used the fact that the volume is 27 yet. So let's use that fact right now to help us find x. So we know that the volume is equal to x cubed. At this moment, the volume is 27. So we have 27 is equal to x cubed. Taking the cube root of both sides, we get x is equal to 3, which we can put in right. We have -1 is equal to 3 times 9, so that's 27, dx dt. Dividing both sides by 27, we have dx dt is equal to -1/27. And the units of length are in feet, and the units of time were in minutes. So this will be feet per minute. So that is it for part A. Part B says find the rate of change of the cube's surface area. So first of all, let S equal surface area. Now let's look back over part A and copy down the inventory that we already know, like dv dt equals -1, volume equals 27, and even just in case we need it, let's write down that dx dt is equal to -1/27. So here are the 4 facts that we already know based on part A, and we are looking for ds dt. So we need a relationship involving the surface area. Well, what is the surface area? It's just the sum of the areas of all of the faces. So for example, if I pick this face, I know that the area of this is just the area of a square, and the side length is x. So the area of this face would be x squared. So let me start my formula. So one face would be x squared for the area. And they're all the same because it is a cube. So it's just a matter of how many faces are there on a cube. Well, think about a die. You know, it's a six-sided number cube. There are 6 of these, 4 faces around the sides plus the top and the bottom. So we will just multiply this by 6, and now we have the surface area formula. So let's take the derivative of both sides and kind of see what happens. On the left side, we just have ds dt. And that is what we are looking for, so that is pretty important. On the right side, we will do the chain rule. So the derivative of the outer function, all right, 2 times 6 is 12, so we have 12x. But then we multiply by the derivative of the inner function, which is dx dt. So let's pause and examine our inventory to see if there's anything that we can plug in here. We know that x is 3. So we can put a 3 in right here. And we know that dx dt is negative 1 over 27. So we can put that in right here. For a free response question, this would be an acceptable answer. Don't forget your units. We're talking about the change in area divided by the change in time. So the units of length for this problem were in feet. So area would be feet squared, and then the time was in minutes. If this were a multiple choice question, you would find this version of the answer among the options.